We talked a little bit about the probabilistic interpretation of the wave function psi. That's one of the really remarkable aspects of quantum mechanics, that there are probabilities rolled up in your description of the physical state. We also talked a fair amount about probability itself, and one of the things we learned was that probabilities had to be normalized, meaning the total sum of all of the probable outcomes, the probabilities of all of the outcomes in a probability distribution has to equal 1. That has some implications for the wave function, especially in the context of the Schrödinger equation, so let's talk about that in a little more detail. Normalization in the context of a probability distribution just means that the integral from minus infinity to infinity of rho of x dx is equal to 1. You can think about that as the sort of extreme case of the probability that, say, x is between a and b being given by the integral from a to b of rho of x dx. In the context of the wave function, that statement becomes the probability that the particle is between a and b is given by the integral from a to b of the squared magnitude of psi of x integrated between a and b. So this is the same sort of statement. You're integrating from a to b, and in the case of the probability density, you have just the probability density. In the case of the wave function, you have the squared absolute magnitude of the wave function. This is our probabilistic interpretation. We're sort of making an analogy between psi, squared magnitude, and a probability density. This normalization condition then has to also hold for psi, if the squared magnitude of psi is going to be treated as a probability density. So, integral from minus infinity to infinity of squared absolute magnitude of psi dx has to equal 1. This is necessary for our statistical interpretation of the wave function. This brings up an interesting question, though, because not just any function can be a probability distribution. Therefore, this normalization condition, treating psi as a probability density, means there are some conditions on what sorts of functions are allowed to be wave functions. This is the question of normalizability. Suppose, for instance, I had a couple of functions that I was interested in. Say one of those functions looks sort of like this, keeps on rising as it goes to infinity. If I wanted to consider the squared magnitude of this function, this is our possible psi, this is our possible psi squared, sorry about the messy there. This function, since it's going to, it's continuing to increase as x increases, both in the negative direction and in the positive direction, its squared magnitude is going to look something like this. I can do a little better there, sorry. If I tried to, say, calculate the integral from minus infinity to infinity of this function, I've got a lot of area out here from, say, 3 to infinity, where the wave function is positive. This would go to infinity, therefore. What that means is that this function is not normalizable. Not all functions can be normalized. If I drew a different function, for example, something that looked maybe something like this, its squared magnitude might look something like this. There is a finite amount of area here, so if I integrated the squared magnitude of the blue curve, I would get something finite. What that means is that whatever this function is, I could multiply or divide it by a constant such that this area was equal to 1. I could take this function and convert it into something such that the integral from minus infinity to infinity of the squared magnitude of psi equaled 1, and it obeyed our sort of statistical constraint on the probability distribution. In order for this to be possible, psi has to have this property, and the mathematical way of stating it is that psi must be square integrable. And all this means is that the integral from minus infinity to infinity of the squared magnitude of psi is finite. You don't get 0, you don't get infinity. In order for this square integrability to hold, for example, though, you need a slightly weaker condition that psi goes to 0 as x goes to either plus or minus infinity. It's not possible to have a function that stays non-zero or goes to infinity itself as x goes to infinity and still have things be integrable. Like I said, if this holds, if this integral here is finite, you can convert any function into something that is normalized by just multiplying or dividing by a constant. Is that possible, though? In the Schrodinger equation, does multiplying or dividing by a constant do anything? Well, the Schrodinger equation here you can just glance at it and see that multiplying and dividing by a constant doesn't do anything. The Schrodinger equation is I h bar partial derivative with respect to time of psi equals minus h bar squared over 2m second derivative of psi with respect to position plus the potential times psi. Now, if I made the substitution psi went to some multiple or some constant a multiplied by psi, you can see what would happen. Here I would have psi times a, here I would have psi times a, and here I would have psi times a. So I would have an a here, an a here, and an a here. So I could divide through this entire equation by a, and all of those a's would disappear, and I would just get the original Schrodinger equation back. What that means is that if psi solves the Schrodinger equation, a psi does too. I'll just say a psi works. Now this is only if a is a constant. Does not depend on time, does not depend on space. If a depended on time, I would not be able to divide it out of this partial derivative because the partial derivative would act on that a. Same goes for if a was a function of space. If a was a function of space, I wouldn't be able to divide it out of this partial derivative with respect to x. So this only holds if a is a constant. That means that I might run into some problems with time evolution. I can choose a constant and I can multiply psi by that constant such that psi is properly normalized at, say, time t equals 0, but will that hold for future times? It's a question of normalization and time evolution. What we're really interested in here is the integral from minus infinity to infinity of psi of x and time squared dx. If this is going to always be equal to 1, supposing it's equal to 1 at some initial time, what we really want to know is what the time derivative of this is. If the time derivative of this is equal to 0, then we'll know that whatever the normalization of this is, it will hold throughout the evolution of the wave function. Now I'm going to make a little bit of simplifying notation here, and I'm going to drop the integral limits since it takes a while to write. And we're going to manipulate this expression a little bit. We're going to use the Schrodinger equation, we're going to use the rules of complex numbers, we're going to use the rules of differential calculus, and we're going to get something that will show that indeed this does hold. So let's step through that. Manipulations of the Schrodinger equation like this are a little tricky to follow, so I'm going to go slowly, and if it seems like I'm being extra pedantic, please bear with me. Some of the details are important. So the first thing that we're going to do, pretty much the only thing that we can do with this equation, is we're going to exchange the order of integration and differentiation. Instead of differentiating with respect to time the integral with respect to x, we're going to integrate with respect to x of the time derivative of this psi of x and t quantity squared. Basically, I've just pushed the derivative inside the integral. Now, notationally speaking, and I'm going to move some stuff around here, give myself a little more room. Notationally, oops, didn't mean to change the colors. Notationally speaking here, the d dt became a partial derivative with respect to time. The total derivative, d by dt, is now a partial. What the notation is keeping track of here is just the fact that this is a function only of time, since you've integrated over x and you've substituted in limits. Whereas this is a function of both space and time. So whereas this derivative is acting on something that's only a function of time, I can write it as a simple d by dt, the total derivative. In this case, since what the derivative is acting on is a function of both position and time, I have to treat this as a partial derivative now. So the next thing that we're going to do, aside from after pushing this derivative inside and converting it to a partial derivative, is rewrite this squared absolute magnitude of psi as psi star times psi. Now the squared absolute magnitude of a complex number is equal to the complex number times its complex conjugate. It's just simple complex analysis rules there. So what we've got is the integral of the partial derivative with respect to time of psi star times psi, integral dx. Now we have a time derivative applied to a product. We can apply the product rule from differential calculus. And what we end up with is the integral of the partial derivative with respect to time of psi star times psi plus psi star partial derivative of psi with respect to time. That's integrated dx. Now what I'm going to do is I'm going to notice these partial derivatives with respect to time. And I'm going to ask you to bear with me for a minute while I make a little more space. It's probably a bad sign if I'm running out of space on a computer where I have effectively infinite space. But bear with me. The partial derivatives with respect to time appear in the Schrodinger equation. I h bar d by dt of psi equals minus h bar squared over 2m partial derivative, second partial derivative of psi with respect to position plus potential times psi. These are the time derivatives that I'm interested in. I can use the Schrodinger equation to substitute in, say, the right-hand side for these time derivatives, both for psi star and for psi. So first I'm going to manipulate this by dividing through by I h bar, which gives me d partial psi partial time equals I h bar over 2m, second partial of psi with respect to x, minus, where did it go? I v over h bar psi. So that can be substituted in here. I also need to know something for the complex conjugate of psi, so I'm going to take the complex conjugate of this entire equation. What that looks like is partial derivative of psi star with respect to time. Now I'm taking the complex conjugate of this, so I have a complex part here. The sign of that needs to be flipped. And I have a complex number here that needs to be complex conjugated, since the complex conjugate of a product is the product of the complex conjugates. What that means is this is going to become minus I h bar over 2m d squared psi star dx squared, sorry I forgot the squared there, plus I v over h bar psi. So I've just gone through and changed the signs on all of the imaginary parts of all these numbers. Psi became psi star, I became minus I became I. And this can be substituted in for that. And what you get when you make that substitution, this equation isn't really getting simpler, is it? It's getting longer. What you get is the integral of something. I'll put an open square brackets at the beginning here. I've got this equation, minus I h bar over 2m, the second partial derivative of psi star partial x squared, plus I v over h bar psi star, that's multiplied by psi from here. So I've just substituted in this expression for this. Now the next part I have plus psi star and whatever I'm going to substitute in from this, which is what I get from this version of the Schrodinger equation here. I h bar over 2m, second partial derivative of psi with respect to x, minus I v over h bar psi. Close parentheses, close square brackets, and I'm integrating dx. Now, this doesn't look particularly simple, but if you notice what we've got here, this term, if I distributed this psi in, would have I v over h bar psi star times psi. This term, if I distributed this psi star in, would have an I v over h bar psi star and psi. This term has a plus sign, this term has a minus sign. So these terms actually cancel out. What we're left with, then, to rewrite things, both of the terms that remain have this minus I h bar over 2m out front. So we're going to have equals to I h bar over 2m. And here I have a minus second partial derivative of psi star with respect to x times psi. And here I have plus psi star times the corresponding second partial of psi with respect to x. And this is integrated dx. Is that all right? Yes. Now, what I'd like you to notice here is that we've got d by dx and we've got an integral dx. We don't have any time anymore. So we're making progress. And we're actually almost done. Where did we get so far? We started with the time derivative of this effective total probability, which should have been equal to 1, which would be equal to 1 if this were a proper probability distribution, but we're just considered with the time evolution, since we know that whatever psi is, we can multiply it by some constant to make it properly normalized at a particular time. Now we're interested in the time evolution. We're looking at the time derivative of this, and we've gone to this expression, which has complex conjugates of psi and second partial derivatives with respect to x. Now, what I'd like you to do, and this is a check your understanding question, is think about why this statement is true. This is the partial derivative with respect to x of psi star d psi dx minus d psi star dx. So, sorry, I'm saying d, I should be saying partial. These are partial derivatives. This is true, and it's up to you to figure out why. But since this is true, what we're left with is we have our I h bar over 2m, an integral over minus infinity to infinity of this expression, partial with respect to x of psi star partial psi partial x minus partial psi star partial x psi. We're integrating dx now. And this is nice because we're integrating dx of a derivative of something with respect to x. So that's easy. Fundamental theorem of calculus. We end up with I h bar over 2m psi star partial psi partial x minus partial psi star partial x psi, evaluated at the limits of our integral, which are minus infinity to infinity. Now, if psi is going to be normalizable, we know something about the value of psi at negative and positive infinity. If psi is normalizable, psi has to go to 0 as x goes to negative and positive infinity. What that means is that when I plug in the infinity here, psi star, d psi dx, and psi, everything here is going to be 0. So when I enter in my limits, I'm just going to get 0 and 0. So the bottom line here, after all of this manipulation, is that this is equal to 0. What that means is that the integral from negative infinity to infinity of the squared absolute magnitude of psi as a function of both x and time is equal to a constant. Put another way, time evolution does not affect normalization. What that means is that I can take my candidate wave function, not normalized, integrate it, find out what I would have to multiply or divide it by to make it normalized, and if I'm successful, I have my normalized wave function. I don't need to worry about how the system evolves in time. The Schrödinger equation does not affect the normalization. So this is that check your understanding question I mentioned. The following statement was that crucial step in the derivation, and I want you to show that this is true, explain why in your own words. Now, to do an example here, normalize this wave function. What that means is that we're going to have to find a constant, and I've already put the constant in the wave function, a, such that the integral from minus infinity to infinity of the squared absolute magnitude of psi of x, in this case I've left the time dependence out, is equal to 1. And same as in the last problem, the first thing we're going to do is substitute the squared absolute magnitude of psi for psi star times psi. The other thing I'm going to do before I get started is notice that my wave function is 0 if the absolute value of x is greater than 1, meaning for x above 1 or below negative 1. So instead of integrating from minus infinity to infinity here, I'm just going to focus on the part where psi is non-zero and integrate from minus 1 to 1. Integral from minus 1 to 1 of psi star, which is going to be a, e to the ix is going to become e to the minus ix, and 1 minus x squared is still going to be 1 minus x squared. Now, I haven't complex conjugated a because part of the assumption about normalization constants like this is usually that you can choose them to be purely real. So I'm not going to worry about taking the complex conjugate of a just to make my life a little easier. Psi, well, that's just right here, a e to the ix 1 minus x squared. And I'm integrating dx. This is psi star, this is psi, integral dx from minus 1 to 1, should be equal to 1. So let's do this. We end up with a squared times the integral from minus 1 to 1 of e to the minus ix and e to the ix. What's e to the minus ix times e to the ix? Well, thinking about this in terms of the geometric interpretation, we have e to the ix, which is cosine theta plus I sine theta. You can think about that as being somewhere on the unit circle at an angle theta. Minus ix, or minus I theta, would just be in the exact opposite direction. So when I multiply them together, I'm going to get something that has the product of the magnitudes. The magnitudes are both 1, and it's purely real. You can see that also by looking at just the rules for multiplying exponentials like this. E to the minus ix times e to the plus ix is e to the minus ix plus ix, or e to the 0, which is 1. So I can cancel these out. And what I'm left with is 1 minus x squared, quantity squared, dx. plugging through the algebra a little further, a squared integral minus 1 to 1 of 1 minus 2x squared plus x to the fourth dx. You can do this integral equals a squared x minus 2/3 x cubed plus x to the fifth over 5 between minus 1 and 1, which when you substitute in the limits becomes a squared. This x part is going to be 1 minus the other limit, minus 1, which is 1 minus minus 1, which is 2. So it's going to give me a 2, minus 2/3 of whatever I get from the x cubed, which is again going to be 1 minus a minus 1, or 2, plus 1/5 of x to the fifth, 1 minus 1 to the fifth, and 1 to the fifth. Again, this is all, basic algebra. Hopefully this is not too confusing by this point. This ends up being a squared times 16 over 15. Now, going up here, if a squared 16 over 15 is going to be equal to 1, a has to be equal to the square root of 15 over 16. That's what it means to normalize a wave function. You have something that you think might be your wave function, but it's not properly normalized yet. So you guess that there's going to be some constant multiplied in, and you write down the normalization condition, integrating your wave function absolute magnitude squared, which usually you will write as the wave function times its complex conjugate. Typically the complex parts of the wave function will drop out, and you'll end up with just something that you can integrate. Proceeding through the integral, you'll end up with some expression that tells you what that constant is. So that's the wave function and how it's normalized. The time evolution of the normalization and the fact that it's not affected by the Schrodinger equation is really a nice feature of quantum mechanics. Otherwise, quantum mechanics would be completely unworkable. A lot of what we've talked about in this lecture has just been how to manipulate the Schrodinger equation, or how to use the Schrodinger equation in manipulations of the wave function. And this is the sort of math that quantum mechanics is all about. There's calculus, there's partial derivatives, total derivatives, integrals. Keeping track of everything is tricky. Well, the result that we've got for normalization here helps. I'm rambling though. At any rate, that's about it for wave functions and normalization. And this is nice because all of the pieces that we've described today all fit together and support this statistical interpretation of the wave function as being related to a probability distribution. We talked a little bit about the probabilistic interpretation of the wave function psi. That's one of the really remarkable aspects of quantum mechanics, that there are probabilities rolled up in your description of the physical state. We also talked a fair amount about probability itself, and one of the things we learned was that probabilities had to be normalized, meaning the total sum of all of the probable outcomes, the probabilities of all of the outcomes in a probability distribution, has to equal 1. That has some implications for the wave function, especially in the context of the Schrodinger equation, so let's talk about that in a little more detail. Of the wave function. This brings up an interesting question though, because not just any function can be a probability distribution. Therefore, this normalization condition, treating psi as a probability density, means there are some conditions on what sorts of functions are allowed to be wave functions. This is the question of normalizability. Suppose, for instance, I had a couple of functions that I was interested in. Say one of those functions looks sort of like this. Normalization in the context of a probability distribution just means that the integral from minus infinity to infinity of rho of x dx is equal to 1. You can think about that as the sort of extreme case of the probability that, say, x is between a and b, being given by the integral from a to b of rho of x dx. In the context of the wave function, This is our probabilistic interpretation. We're sort of making an analogy between psi, squared magnitude, and a probability density. This normalization condition then has to also hold for psi. If the squared magnitude of psi is going to be treated as a probability density. So, integral from minus infinity to infinity of squared absolute magnitude of psi dx has to equal 1. This is necessary for our statistical interpretation. That statement becomes the probability that the particle is between A and B is given by the integral from A to B of the squared magnitude of psi of x integrated between A and B. So this is the same sort of statement. You're integrating from A to B, and in the case of the probability density, you have just the probability density. In the case of the wave function, you have the squared absolute magnitude of the wave function.